the Nomenclature National Soil Moisture Workshop, which is a result of the partnership with, at that point, the National Soil Moisture Network effort that had started separately among some universities and federal agencies. So we are at the National Soil Moisture Workshop. I think this is our 3rd year calling ourselves that, maybe 4th, and I think it's 4th. And welcome. This is an opportunity for the soil moisture community to get together and share knowledge and see the latest and greatest that's happening in the research community. This is designed for researchers, but hopefully it's helpful for operators and action agencies, as well as community groups and folks that want to see or just have a general interest in soil moisture. This is a 2-day workshop that will be spread across 8 hours. We do have a happy hour this evening, more social atmosphere, but we like to think the entire time is social, giving everybody a chance to kind of relax, listen to some good talks, interact with folks. You can interact in the chat. We'll have a poster session tomorrow with other opportunities for more direct interaction as well. And it's an opportunity for us to just absorb some information, hopefully, and enjoy our time together here. As part of that, we're trying out a few things. As always, we don't have conferences perfected, so we'll be doing some polling. We'll be doing a Jamboard. This is an opportunity for folks to converse about different things. I'm going to post that in the chat right now. The Jamboard, let me see if I can share it. If you haven't seen this Jamboard before, Jamboard is hosted on Google, and it's a simple post-it note system where you can add a note over here to the question on this page. And the question here is, what's a challenge you face in your everyday soil moisture research? Here someone has put the funding as a major concern. I think everybody would agree to that. We have 4 pages total. Another question is, what's the next big thing that soil moisture science need to focus on? As well, in the year 2051, what does soil moisture, this is kind of a science fiction concept of, imagine what could happen. What would be an ultimate goal if you had every wish fulfilled as far as soil moisture monitoring? What would that look like? And it'd be interesting to see what folks consider as an ultimate goal. And then a little more fun is, what are you listening to, watching, or reading that you would recommend? These are the things that you would probably find out as you went and got coffee in the back of the room. And we don't have coffee in the back of the room because that's my bedroom, and you're not here. So we're not going to be able to do that. So this is a place for that to happen. So if you want to partake during the session, before and after, tomorrow, this will be open, and we'll try and post as much as possible as a reminder. Now, our first speaker today, our kickoff speaker, is Dr. Stephen Evett from USDA ARS in Bushland, Texas, which I've been told is West Texas. And got to make sure you get your Texases right. If you know anybody from Texas, you know that to be true. So with that, we'll continue to have people enter, and please, Steve, take it away.
Can you see my screen, Mike?
I can see your screen.
Are you ready for me to start?
Yes, go right ahead.
Thank you, Mike, and thank you for the organizing committee for asking me to give this talk to start things off. In a somewhat rebellious mood, of course, I've changed moisture to water, but Mike understands that. I'll start off with a little history. Farmers have known about soil water status for as long as they've been farming, because they've recognized that plants don't grow well without good soil water. There's evidence of thousands of years of irrigation that is a result of that recognition of the importance of soil water. That continues to this day. In 1962, the USGS published a book, essentially, mostly by Johnson, that described methods of measuring soil moisture in the field. That was an important book that brought together a lot of ideas, a lot of the literature, and informed quite a few people as to what was available. Of course, for a long time, we've had that look and feel method from NRCS, very notable to our agricultural community. Soil coring for volumetric soil samples is still the standard for actual measurement of water content. Anything else is sensing. And that goes back way, way back. But the King tube, which is still in use, was invented in 1980 or 1890. So there's a long history of doing this. Weighing and weighable lysimeters can be used to monitor the soil water storage and changes. Since at least the 17th century in this country, Briggs and Chance did some famous work early in the last century in Colorado, using weighable lysimeters to determine crop water use and the crop water productivity. Heat diffusion methods have been around for a long time, so have resistance blocks. In the granular matrix sensor, which is an improvement on the gypsum block, was patented in 1985. And intensitiometers have also been around for a long time. Most of these methods are not used in routine soil moisture monitoring today, with the possible exception of resistance blocks used by some networks. Due to the advances in nuclear physics before and during World War II, the understanding of neutron interactions with atoms was greatly increased, and the neutron probe was invented probably by Pieper in 1949. Gardner in 1952, Wilfred Gardner published on that, and in soil physics literature is usually regarded as the father of the neutron probe. It's used at depths in greater than 200 feet for assessing medium water contents. Of course, it has to be specifically calibrated for the medium, but it remains a useful tool. Commercial systems for use in agriculture and other uses, environmental monitoring, construction, seepage in dams, were introduced in 1955 by Nuclear Chicago, followed by Troxler Electronics and Campbell Pacific Nuclear in this country, and systems in England, France, and other countries. And staying on the theme of neutrons, cosmic ray observing system was developed in the early 2000s. And I've just realized I have to silence my phone. So I'll take a minute to do that. Sorry. I'm not going to speak much about Cosmos, but I will talk about other sensing methods. But Johnson concluded that the gravimetric method was the most satisfactory method for most problems. But the radioactive method was normally best for obtaining repeated measurements of soil moisture in place. He concluded that all methods have some limitations and that the ideal method for measurement of soil moisture under field conditions is yet to be perfected. And that statement would stand today, in my estimation. Capacitance methods for soil water sensing date well before Anderson's paper in 1943. The capacitance methods were used for building material moisture estimation. Previous to that, Wabshall's paper in 1978 is frequently cited for his in-depth work on frequency responses to moisture. But it was Dean, Bell, and their co-authors in 1987 who really first published on a dual cylinder capacitance sensor that could be placed in a plastic access tube and used to monitor soil water content at different depths. That was actually post-dated, the popularization of time domain reflectometry by Clark Top and his co-authors in Canada in 1980, which started off in both those senses, both capacitance sensing and time domain sensing, real innovation, and a period since then of very rapid change in what's available for soil water monitoring. Remote sensing approaches based on passive microwave responses and active radar, aerial resistivity, and other airborne systems will be discussed by others in this workshop. I'm not going to address those, except to say that in situ sensing is often used necessarily for testing the effectiveness of the remote sensing approaches. But since 1990, with the advent of the cell phone industry really getting underway, there have been great advances in cost, ease of use, power consumption, and telemetry. The GSM standard for mobile phones was approved in 1987. That was a worldwide standard that really kicked off the cell phone industry. But those high frequency chips found their way into wireless node and gateway systems, cellular network-based data transmission, and data in the cloud for access from practically anywhere. And this has been around for a while. The SCAN network, for instance, that NRCS runs, uses meteor burst satellite and cellular telemetry, depending on the site. Well, what are the principles of soil water sensing? Well, soil water sensors do not measure soil water content. Measure surrogate properties that are then related to water content through a calibration. Capacitance methods use a variable resonant frequency and varies with water content. Phase delay uses a constant frequency, but measures the phase delay, which is then related to water content. Transmission time sensors, both time domain reflectometry, time domain transmission, and the quasi-travel time sensors provide some measure of the travel time of an electrical pulse along a rod or waveguide in the soil. And that is related to water content. And then, of course, the neutron count has been around for a long time as a fundamentally different way of assessing soil water content. All of the electromagnetic sensors are related to what they measure is related to that apparent dielectric permittivity, which increases with water content. But apparent dielectric permittivity of soil also changes with bulk EC and bound water content, which themselves change with the absolute water content of the soil, its temperature, its salt content, and the content of active clays. So this is a sticky wicket. And where the sticky part comes in is in the fundamental physics behind these measurement systems. Any capacitance sensor is based on determining the capacitance, and the capacitance is a function of Gauss's law, where the capacitance equals a geometric factor multiplied by the apparent permittivity. That geometric factor depends on how the electromagnetic field from the sensor permeates the soil and any surrounding materials. It can change, and as it changes, the capacitance of the soil sensor system changes, and the frequency that's measured changes, which would mean a change in the water content for most systems. Time domain reflectometry, on the other hand, is related to the permittivity as the square root of the permittivity multiplied by the magnetic permeability, which is usually taken to be 1, but can change in some soils. Note that in the time domain physics, there is no geometric factor. So that travel time is not dependent on how the field permeates the medium around the rods of the time domain reflectometer. This is a key difference and really why there are large differences in the capabilities of these systems. And I'm going to talk about that to some extent today. Schwenk, Tim Green, and their co-authors studied the electromagnetic field around plastic access tube within a fluid. This was, forget the fluid, but they studied this, they modeled it, and what you see on the right are modeled electromagnetic fields, but then they took measurements to verify that the model was correct. And what they found is that as a conductive element was placed closer to the capacitance system, the field was distorted by the conductive element. And we know this is true. As soils get wetter, that field shrinks and changes in size, but it can also change in shape. And here's an example of this. This is modeled after a double cylinder capacitance sensor shown on the right. And the top figure shows that sensor in a plastic access tube in a uniform medium, where the field uniformly permeates the medium. If the medium around that access tube is not uniform, if for instance it has some PEDs that are blocks of soil, it has some PEDs that are wetter than others, that field will preferentially invade the wetter PEDs, and it will be non-uniform. That means that the geometric constant changes because wetter PEDs are more conductive. This means that the frequency response will change. And even though in the lower figure, the average volumetric water content is the same, the lighter color is drier, the darker color is wetter. Even though the water content would be on average the same, the reported water content would be quite different. And we see this in experiments done in the field. This sort of thing was verified by many authors in the electronics literature, but also by people in soils such as Sally Logston, who rather famously, in my view, illustrated this with a capacitance sensor in a soil that was consisted of alternating blocks of drier and wetter material, and got one reading, and then mixed the material so that this water content was the same, but was uniform, and got a quite different reading. So how does TDR work? Well, TDR probe, the old kind, what we call conventional TDR, consisted of a coaxial cable, a handle, and 3 rods, sometimes 4 rods, sometimes 6, but classically 3. And the center conductor of the coaxial cable was connected to the center rod. The outer braze was connected to the outer 2 rods. And when the distance between the outer conductor and the inner conductor changed, you got an impedance increase, which in the waveform that you see in the lower left figure, that's represented by this bump, an increase in impedance. In this probe in air, as that pulse entered the waveguide in air, this waveform would actually have increased. But because this waveform was taken in wet sand, it decreased due to the wetness of the sand and the larger apparent permittivity of that sand material. And then it goes along and it gets to the end of the waveguide, and that's an open circuit. So the pulse is reflected, and you see that reflection here at the end of what we call a TDR waveform. The upper line is the first derivative of that, which is often used to help analyze the waveform. This time 2 and time 1 are the travel time equaling the difference of those. And that is linear in water content for most soils. It can be used to calculate the apparent permittivity. Importantly, in many soils, as they get wet, they become more conductive. In this soil, as you go from 2.5 centimeters to 25 centimeters, the soil is wetter. It's also more dense, and the conductivity goes from 0.04 decisiemens per meter to 1.36 decisiemens per meter. And the sharpness of this reflection at the end of the rods decreases as the conductivity of the soil increases to the point where it may become difficult to find time 2. Now, with good TDR methods, we can operate in most soils and find time 2. With newer methods, we can do even better, and I'll show you that later. But our low-cost water content reflectometers, the CS616, the Trime tube probe, and similar sensors, some of which claim to be TDR sensors, operate quite differently. What they do is they inject a pulse into a waveguide or into a conductor in the soil, and then they compare the reflected pulse strength against a threshold voltage using a cheap electronic component called a voltage comparator. That means that they don't trigger recognition of a reflection until that reflected voltage reaches a certain amount, a certain value. So they don't find time 2, they find something that I'll call time 3, which is the wrong travel time. Now, if that were wrong in the same manner all the time, that wouldn't be such a big problem. But the fact is, it's wrong differently depending on how wet the soil and how conductive the soil is, because this slope increases or decreases rather as the soil becomes more conductive, meaning that this time 3 becomes a larger value for the same water content. So that's why these water content reflectometers often have problems. And here's an example for the CS616. The porosity of this soil was about 0.42, and the blue boxes here represent what the possible water contents were. The TDR water contents, this is measured with conventional TDR, are shown on the x-axis, and the CS616 water contents are shown on the y-axis. For the 6 centimeter data, what we see is a lot of scatter here caused by temperature cycling. Temperature cycling means that we have cycling in the bulk electrical conductivity, which increases strongly with temperature and decreases strongly as temperature decreases. In a dry soil, this is 2 centimeter data, clear near the surface, smaller bulk density, and a smaller bulk electrical conductivity, we get closer to a 1-to-1 relationship, but still with some scatter. And when we go deeper to 12 centimeters, where the soil was wetter, had more clay in it, and had a larger bulk density, and thus a larger bulk EC, the water contents from the CS616 greatly exceeded the possibility, which is one reason why quality control should look at the porosity of the soil. So there have been a lot of comparative studies. They're still going on. I'm still doing some work in that regard. But early in the game, the International Atomic Energy Agency and FAO recognized the neutron probe as a good method for use in studies of agricultural water consumption. The water pulled out of the soil by a crop, the water added to the soil by irrigation. But the advent of the capacitance sensors in the 1990s made the IAEA question whether the neutron probe was still what they should be promoting. So they brought together a panel of scientists who were experts in soil water measurement or sensing using time domain reflectometry, capacitance, and neutron thermalization methods. Clark Top was in that group. I was in that group, as were folks from France, Australia, and at least one other country I've forgotten. Oh, from Austria itself. What they concluded was that the neutron probe should remain the recommended method by the IAEA, despite the fact that many people were speaking out against it due to the fact that it has a radioactive source. The reasons were the method measures a relatively large volume. That's compared to TDR and capacitance instruments. It's reliable and easy to use compared to others at that time. That was still true. And the technology was mature and had a large knowledge base. I would add to it that the large volume of measurement makes field calibration much easier than it is for TDR capacitance sensors. So this conclusion was based in part on some studies we did in the early 1990s on the Troxler Century 200 AP, which went down a plastic access tube. We used 6 Troxler 200 AP sensors, 4 neutron probes, 2 of them Troxler, 2 of them Campbell Pacific Nuclear, and did a wet site, dry site calibration in a deep soil. And the result you see in the left figure, you see the water contents in the wet site and the water contents in the drier site for the neutron scattering, and a large R² value, a small root mean squared error. And then for the capacitance sensing, we see a much larger root mean squared error, much larger 95% confidence intervals. And we see some values of the D value, which is a sort of a frequency scaled frequency value, that were larger for the dry soil than they were for the wet soil. Now, this was very confusing, but NRCS had reported to us that sometimes their sensors would tell them the soil was wet when it was dry, which is why we did the study. One thing we did is we calculated the mean D value from all the soils and then plotted the D values for the individual sensors against that. And we got a very consistent slope near 1 and high R² values. What that told us was that the capacitance sensor was responding very reliably to some feature of the soil that wasn't just water content. This was, I believe, the first evidence that small-scale variability around access tube affects capacitance sensors. And we suspected that bulk EC was involved. Or at least we questioned that. A lot of other studies were done. This is Paltanano and Starr determined that 93% of the response of a capacitance sensor, in this case, a Centec and Varoscan, was within 3 centimeters of the access tube. We measured the vertical response and found that 90% of the vertical response was within the sensor height itself. We did this for several capacitance type sensors and for the TRIME quasi-TDR sensor, and found that the volume decreased as the soil became wetter. And in many cases, the volume was smaller than the height of the sensor rings itself. This means very, very small sensing volumes, which means any variability in soil water content would be captured, and you would get lower readings. Here's a comparison of volume sensed. Neutron probe senses between 14,000 and 65,000 cubic centimeters. TDR, 20 centimeter probe, about 360 to decagon 5TE, which Robert Schwartz has worked with quite a lot, 60. And the double ring capacitor, 250 to 600 cubic centimeters, which isn't too bad, yet it acts as if it's much smaller. So what's going on there? We wanted to know, so we did some tests in the field. One of these was done in California with some folks that came over from the Middle East and worked with us for a year. This was a deep soil. It was drip irrigated, and it had salinity that increased with depth. Yet it was a very high producing field, so the salinity wasn't inhibiting production. Very common in California to have soils like this. The neutron probe had essentially depth invariant calibration, maybe a slight difference between two deep layers. And of course, quite a different calibration for the 10 centimeter depth, which is common with neutron probe. The delta T PR26 was all over the place, but essentially slopes increased with depth, and the intercept increased with depth as well, or actually decreased with depth. So you got a whole scatter of different calibrations. The same thing happened with the Diviner 2000 and the EnviroScan, which are very similar in how they work. They're capacitance sensors as well. Slopes increased, calibrations increased with depth. Now, if this were reproducible across the field, it would maybe be okay, but in fact it isn't. It changes with the distribution of bulk EC at every point in the field, making these sensors essentially unusable in this situation. Now, the tremendous interest is shown by this group in monitoring Vadose zone, increased with our societal interest and with certainly climate change effects and increasing drought. Sensing systems relying on soil electromagnetic properties are first amongst those of interest. And our special issue in 2005 from the Vadose Zone Journal consolidated several reports on this. From that issue, the chief problems found were susceptibility to interference from soil electrical conductivity and temperature, which influences electrical conductivity. It's not a temperature effect on the electronics themselves. It's a temperature effect on bulk EC, which are related to salts and clay content and type and bulk density. Bulk EC goes up as density increases, and the small measurement volume, except for GPR. The IAEA, after its 1998-99 meeting, pushed off a 5-year study that resulted in a 2008 book that came up with 4 conclusions. One was that the field calibrated neutron probe remained the most accurate and precise method for soil profile water content determination in the field and for use in their projects. The capacitance sensors exhibited much more variability in the field than either the neutron moisture meter or direct soil water measurements, and were not recommended. This wasn't just my research. This was research by people on 4 of the continents. All sensors must be field calibrated with the possible exception of conventional TDR with waveform capture and graphical analysis. And none of the electromagnetic or nuclear sensors studied was practical for on-farm water management due to either inaccuracy, cost, or difficulty of use. At that time, conventional TDR was still quite difficult to use. Here's some field comparisons. I'll try to go over this quickly. Here's the neutron moisture meter results in a dry land on the left, irrigated winter wheat on the right. showing clear differences. The gravimetric differences were also fairly clear, but these are fairly small sample sizes, so there's more noise in it. The TRIME T3 initially showed pretty decent differences, later degraded in other studies. And the EnviroScan, Diviner, and PR16 all showed a lot of noise, which is seen in the standard deviation plots on the left. We put these in the field in transects of 10 access tubes and 10 locations of gravimetric readings, and did these measurements over time and used relative difference ranking to identify variations in space and time. The variations in time are seen by the vertical bars. Larger variations indicate larger variation in time. Variation in space is shown along the x-axis. So we see very little variation in space in the dry side with gravimetric readings, a little bit more on the wet side because we had some runoff. Neutron moisture meters showed essentially the very same pattern in space, but less difference in time, probably because of its larger volume of sensing. The EnviroScan showed a much different picture. It showed more variability in time and also more variability in space. This is false variability. This didn't really occur. We believe this occurs because of the differences in soil structure around each access tube. Even on the wet site, it's more variable, although not a lot more. The Diviner showed the same pattern, a little bit less. The Diviner is a higher frequency device than an EnviroScan and should be a little less sensitive to these EM variations. The TRIME and the PR16 both showed more variability on the dry side than actually existed in the field by measurement. We repeated this in 2004 in a soybean field that was fully irrigated on the right side shows that, and deficit irrigated in half of it, 10 access tubes in each half. The neutron moisture meter showed this kind of variability. The TRIME showed somewhat more. Here's some of the TRIME points way down here, falling off. The EnviroScan, the Diviner, showed, our PR16 quit working, showed much more variability on the dry side and somewhat more variability on the wet side than the neutron moisture meter. And then after fallow in early 2005, we continued this and found that basically there's little difference in profile water content assessed by gravimetric sampling or by the neutron moisture meter. This is down to 2 meters. But the EnviroScan, the TRIME, and the Diviner all showed spatial variability in the water content. Now, what does this mean? What it means is we can't rely on these sensors. We would have to have a whole lot of them to get a mean value that means anything. It also means that if we're trying to use sensors that are capacitance-based to assess variability in soil moisture to, for instance, verify that a satellite remote sensing result is correct, we have to deal with this spatial variability that is non-existent, unreal, and factor that into our thinking as to whether we have a good verification or not. Now, in this study, we again compared the EnviroScan to the Diviner. As we compared the Troxler AP200s to each other, we did this again in these same access tubes. And despite the fact that there is so much variability in the water contents, we got very strong correlations. These are readings up and down these access tubes and 10 access tubes. Very strong correlations, a little bit more one-to-one when we use the soil-specific calibration, but very strong nonetheless, which means there is a very reproducible response to soil properties that are not water content alone. And this is the fundamental bugaboo of capacitance methods. So what are the challenges do we have? Well, unattended data acquisition is required these days. We don't have the labor to do it manually. Wireless data telemetry is also required. We need to be able to do this remotely. Low cost is required. Conventional TDR, neutron probe both fail this challenge, although capacitance sensors tend to meet it. But TDR advances are meeting the challenge, and low power is required, which most sensors can meet that requirement. In 2015, we came out with a directly coupled TDR sensor, which combined a computer, a TDR instrument, a probe, and temperature sensor into a single sensor that costs a little bit more than $200. Based on a circuit like this is the first circuit that was developed. It was used in a cylindrical hollow tube for a waveguide on access tube saltwater sensing system. And then this circuit was developed to be put into the TDR-315. So this made a great advance in the usability of TDR methods. And the improvement of this direct coupling of the TDR circuit itself to the waveguides is illustrated in this figure from Robert Schwartz. Conventional TDR in a very wet clay soil produces a reflection like this, where time 2 is determined to be here by waveform analysis, and there's a lot of scatter or imprecision in knowing that. Whereas the TDR-315, because it's directly coupled and there's no signal lost on a long coaxial cable, produced a very discernible reflection in a much smaller travel time. And this has turned out to be a much more accurate way to assess saltwater content. On the right, I'm just showing some figures of the waveguide on access tube that Joaquin Casanova developed with us, and that is under development now by Climate Incorporated. Some outstanding questions that we still have are: can deep dense profiles VM sensors determine soil profile change in storage, as well as the weighing lysimeter? What data standards should be in place? What water sensor installation practices are best? What are siting requirements? Many on this call have been involved in discussions of this. I want to talk a little bit about resolving the soil water balance. When we studied the Cosmos system, we had 16 profiles of water content sensors to a meter depth and compared them with neutron probe readings. And this top green line is the 0 to 1.15 depth range profile water content, which match the neutron probe readings very well. Those are the black circles. And when we compared EM sensor storage change to neutron probe storage change, we've got a very nice linear response. So we believe now that this can be done. And we followed that up with a study where we have three profiles of TDR sensors in a large weighing lysimeter. You can see the depths here. There's 15 sensors throughout the depth of the weighing lysimeter. And this is the kind of results we got. Good linearity. Some calibration issues were not on the one-to-one line. Comparing the lysimeter relative storage to the TDR profile water content, we got a very linear response. But again, some calibration issue, which I believe is due to the TDR-310S sensors used. And here's more. This is a surface to 2.3 meter profile comparison against fairly high R squared, but same calibration issue. In this slide, I threw in just so that people understand. This dotted line is the mean of 3 of the TDR sensor profiles. And these two lines with open circles are the neutron probe water contents. Even though the storage and the storage change in the profile are quite similar from the TDR and the neutron probe measurements, the individual depth-wise comparisons cannot be made because a neutron probe is smearing water content from a large volume, whereas the TDR sensors are essentially point measurements. Some people have tried to do field studies where they compared sensors against neutron probe, and that you just can't do that. Well, we've all talked about data standards and management. They exist, they're not universally accepted. In our development of a node and gateway system, one of the things that we have focused on is that data should be self-referential so that anybody looking at the data knows what the data logger was, what its firmware version was, what its location was in space, what its elevation was, etc. This is data logger. All the sense parameters from the data logger as well, and the time in coordinated universal time. For the gateway, most of those plus the received signal strength for both the nodes and the outbound connection. The sense parameters should minimally include soil water content, apparent permittivity, temperature, bulk EC, and the travel time or the frequency, whatever was actually sensed, so that an ad hoc post-calibration can be done. And then data storage and archiving on secure servers with backup or remote access are essential. I'll close with describing this node and gateway system during the polar vortex in February that came down through Texas. We're about here. We were below zero for some 16 days, below freezing rather, for some 16 days, got down to minus 24 degrees C, 2 snowstorms, and the data came through this system's very robust system. Although I would say we're still working to make the firmware even better. I've already been through this. Summing up, new sensors and sensing systems arrive frequently. Most use capacitance technology and suffer from its limitations. We should be very careful. Progress on in situ soil water sensing networks is steady, as all of you know. TDR sensors using waveform analysis can deliver accuracy enough to replace weighing lysimeters and neutron probe and inform irrigation decision support systems and provide ground truth for remote sensing studies. And data standards and data management standards are progressing. And I believe I've gone well over time, but I thank you for your attention.
Thank you, Steve. And I posted the IAEA, a link to the IAEA in the chat, along with the strategy document for the NCSMMN, for those that feel like clicking through. Do we have any questions for Steve? And just to set the stage, we have an hour gap in an hour and change. So we're just gonna let everybody breathe as far as their presentations go. So if we're off by a couple minutes, we have plenty of time to make that up. So our goal here is to really have conversations. So do we have any questions for Steve? If you can't think of them now, he'll also hopefully be in the chat later and you can pick on him there. I'll ask a question. For the monitoring through depth, what do you find for your stakeholders? What are the depths that they're really, or volumes, or sequences of depths are they most interested in?
Well, most of my stakeholders are all over the map. So that's a question that's very difficult to answer. If I define my stakeholders as agricultural people, well, then it's the active root zone, which for many of the crops can extend down to 1.5 meters. So that would be important. If my stakeholder is someone who wants to close the soil water balance for evapotranspiration calculations, then the profile is quite a bit deeper because you have to get down below, well below the active root zone and the zone of root water uptake to close the soil water balance sufficiently to get accurate ET. So you're talking more like 2.5 meters. If you define my stakeholders as those who want to work above a karst aquifer in shallow soils, well, it's down to the rock, which might be only a meter down. So there is no real answer to that. But I think a challenging question would be, how can we close the soil water balance well enough to get accurate crop water use estimates or accurate estimates of water consumption in any environment?
Okay. Kevin Brinson of Delaware asks, if you were advising a network looking to add affordable soil moisture sensors right now, what would you suggest? And secondly, what are the essential steps a network should take in order to obtain acceptable quality soil moisture data with the sensor suggested?
Well, now that we have an accurate TDR sensor that actually captures a waveform and analyzes it for travel time, I would suggest using it. I know there's only one manufacturer at the time, but the sensor is relatively inexpensive when you consider the entire cost of acquiring and managing data. One of the things I've learned along the way in my 30 plus years with ARS is that spending little on equipment initially causes great costs later on in repeated effort, in failed efforts. So I would urge people to use something that they know is going to work well, and that would be the true TDR sensors. I wouldn't recommend any of the capacitance sensors. There's still a lot of work being done there. Maybe something will come up, but the fundamental physics argues against it. And what we know about variability on a very small scale, it just argues against it.
Okay. We have some questions clicking through, and they're actually so numerous, I don't know if we can get to every single one. So what I'd rather have you do is, starting with Ron Leeper, go through now and on your own in the chat and have these conversations. And we'll move on to our next speaker. So thank you very much, Steve.
I will do that. Well, thank you for the opportunity. And one of the things that Mike asked me to do is be inspiring. And the next comment, it says I'm depressed. So I guess I didn't meet that requirement. Thank you.
You put some smiles on some faces. So I think you did a good job. And certainly makes us think more deeply about how we monitor soil and what we believe electronics tell us. So we will move on now to Kat Weckman. Sorry if I say your name wrong. Kat, you are here somewhere. I saw you before.
Yeah, I'm here.
You're going to share your screen.
Yeah, I'm just going to share my screen. And I'll ask you all. Let's see. Is it in?
It's in full mode. So
full mode. Okay.
You're good.
Oh, it skipped my first one. Let's go back. All right. Thanks, everyone. I will try to stay on time just because of running over a little, but thanks, Steve. That was a really interesting presentation. I learned a lot. My name is Catherine Wickman, and I will be giving a short update on the Upper Missouri River Basin Plains Snowpack and Soil Moisture Monitoring Network today. I'm telling you a little bit about our siting criteria, especially as it relates to soils. And this project, the lead agencies, the Army Corps of Engineers and project managers are in the Omaha district, but I work for the Center for Integrated Research on the Environment out of the University of Montana. We're contracted by the Army Corps as a coordination agency. Just a little background on the project, how this network came about. After the historic floods of 2011 in the Upper Missouri River Basin, the Army Corps and various basin agencies developed a framework called the 2013 recommendation for the establishment of the Upper Missouri River Basin Plains Snow and Soil Moisture Monitoring Network. And the technical review panel found limitations in the plains, specifically in the snowpack and soil moisture data, which led to under forecasting of that 2011 runoff. And so this left a need for increased monitoring across the basin. And so this recommendation got to legislation and was authorized under WRDA, or Water Resources Reform and Development Act, which is the primary legislation by which Congress authorizes Army Corps projects. And the Army Corps of Engineers was designated as the lead agency on this effort. Additional authorization occurred in 2020 that authorized Army Corps to coordinate with other federal agencies, including NOAA and NRCS, USGS, and USBR for continued installation on this network. And data obtained from the network will be available to a wide range of stakeholders. And specifically, the Army Corps Northwest Division of Water Management will utilize the Plains snowpack and soil moisture data in its runoff forecasting for reservoir operations. I'm gonna move this, sorry. And the, oh yeah, so they'll use that for forecasting reservoir operations. So installation of the network will be done by these mesonet groups, they're called, which are these climate and weather stations that exist within each state in the basin. And even though Army Corps is the lead agency on this project, they're not necessarily the experts on this type of data. And so it was advantageous and made sense for the network to utilize these existing networks that can be upgraded or expanded. And these mesonets have amazing institutional and legacy knowledge within the states and understanding basin stakeholders. They have existing relationships with landowners. And so it made a lot of sense for the success of the project. So what happened is each of these 5 state mesonets, which work within the universities, were awarded contracts, and then annually they're awarded these single award task order contracts, or SATOCs, depending on funding and sites available. The total capacity for the project is about $51 million, and a small portion of that has been awarded to this date. We will be awarding about 45 sites coming up for fiscal year 2021. And currently this summer, we have about 40 sites being installed, with about 2/3 of those done already. NRCS also plays a role on this project. They'll be managing the soils portion of the project. So soil sampling and characterization, which we'll be doing at their lab in Lincoln, Nebraska, and then also helping with the benchmark soil analysis, which I'll talk a little more about. And then our group, the Center for Integrated Research on the Environment, we're helping with day-to-day coordination services, helping to establish a workflow for site selection and data transmission, and working with the data site database. So I just wanted to show you a quick glimpse of what these weather stations look like and what we'll be collecting. So we'll collect 5-minute air temperature, relative humidity, solar radiation, wind speed, wind direction, and precipitation, as well as 60-minute snow depth, including images every 60 minutes that will be posted on websites, and then 60-minute soil temperature and soil moisture. And because this is a soil moisture workshop, I figured I better show you what we're using in the ground. And this is an image at one of the pilot stations in Montana. And it shows the soil moisture probes installed. This site's unique because they were actually wanting to do an in-field comparison of a couple different types of probes. And so there'll normally only be one set of probes, but these are installed at 5 different depths within the soil column, 5, 10, 20, 50, and 100 centimeters. It does depend on the depth of the soil, and they'll be collecting 60-minute soil temperature and soil moisture measurements. And we actually are using the probe that Steve mentioned in his presentation, or some of the mesonettes are using this probe, the Aclima TDR probe. I don't know a lot about the different models. And then some of the mesonettes are using a Stevens hydro probe, which I am not sure the technology on that one after listening to Stephen's presentation there. So moving into our site selection process a bit, we've been working on this process. It's a dynamic and changing process because we're still testing it, but the overall goals are to help systematize our process of nominating, assessing, and selecting new sites across the basin, standardizing the assessment of criteria and constraints for each site, and then facilitating and streamlining the site selection process through an annual cycle. For today's presentation, I'm just focusing on the siting piece, so I won't be boring you with every single part of our process. Before we can think about criteria, we had to think about what our unit of analysis is and what how we're spatially distributing these sites across the basin. So we chose to utilize a grid to spatially distribute the 540 stations across the approximately 300,000 square mile basin. And we chose an Albers equal area projected square grid that's adjusted to align with the vertical borders between Montana, North Dakota, South Dakota, Wyoming, and Nebraska. And a projected grid helps us preserve the area of the cells as we move east and west and north and south across the basin. So we end up with approximately, or exactly 540 square grid cells that are 500 square miles in area. And these, this grid also helps accommodate our station spacing requirements, which I'll mention more later. This helps just zoom in a little on one of the states so you can get a better look at that grid. So this is South Dakota. You can see it aligns along the vertical border here. The horizontal borders are not aligned because we can't really get both to align. So we just have rules to help decide which state each grid gets assigned to. So the idea is that each grid will have one station, or each grid cell, sorry. So now that we knew our how we were spatially distributing the stations and what our kind of unit of assessment was, we could think about our siting criteria. And so we split that up into 3 tiers. Tier 1 is pretty basic. It's across grid cells, and essentially we just want to make sure that when we're looking at a candidate site, it's within our project area. So very basically located within the Plains region of the Upper Missouri River Basin and located in one of the major states within the basin. So Montana, Wyoming, North Dakota, South Dakota, Nebraska. There are small slivers, as you can see in Minnesota and Iowa here, which we will be putting a couple sites in each of those states, probably implemented by the mesonettes we're already working with. And we'll kind of deal with those later on in the project. So then we look at our tier 2 siting criteria. So now we're looking within the cell. Once we're within a cell, what's an appropriate place to put one of these sites? So we want a site that's relatively flat. So you're looking at the topography, roughly less than 7 degrees in slope, surrounding area within an elevation below 5,500 feet. That's what we use to define the plains area. Representative of dominant soil type, which I'll talk a little bit more about in a bit. And then between 15 to 29 miles from a surrounding station. So we want to avoid stations being really clustered together or really far apart, which leads to the last criteria for this one, which is that they're relatively centered in the grid to create this even spacing across the network. That's a pretty subjective one, so we're still working with it, but the idea is that, yeah, you'll have this even spacing of sites across the network, and that's especially important for some of the modeling, specifically the snow water equivalent modeling that NOAA is doing. It's important we kind of have this even spacing. And then lastly, we have the tier 3 or within grid cell fine scale criteria. So this is getting down to the nitty gritty of once you have an area, you decide, or a few areas, you know, I want to put a site here. You have to think about those really important administrative criteria, such as land ownership, and can I get an agreement from this landowner at road access, cell reception, so you can transmit the data. For these weather stations, you have to think about distance to any sort of obstructions or water bodies. They deal with a lot of vandalizing issues, so possibility of negative human interaction needs to be considered. And then within the site, you have to look at your microtopography and slopes, your soil type, and last but not least, the environmental and cultural regulations that need to be considered, thinking about wetlands and habitat and cultural artifacts or historical areas. Trying to keep an eye on my time here. So getting back to the soils piece, which was a part of that tier 2 data, we knew we wanted soils to be, we wanted to represent soils evenly across the basin, but that was kind of easier said than done. So we had to think about, well, how do we do that, and how do we assess what a representative soil is? We were really lucky to have NRCS on board with us. And so one of their GIS specialists and soil specialists helped us to build this benchmark soils tool, which is in the way of a raster layer that's used to target areas within cells that have representative soils. So what they do is identifies areas within the grid that has representative soil type based on these what are called soil landscape types, and then more detailed data from the GNATSCO database. And the 6 soil characteristics we're using when looking at representative soil is soil parent material, geomorphic landform, percent clay content in the upper part of the soil, percent clay content in the lower part of the soil, depth to root restrictive feature, and then the soil taxonomy grade group classification. And just basically the cartographic model developed for this analysis had 2 main steps in its production. So the first is to summarize the predominant soil characteristics in each HUC 8 watershed, which is our chosen unit of analysis. And the reason we summarized by watershed and not grid cells is to better capture that range of soil characteristics across the basin. So if we just summarize by cells, we'd end up placing sites in the same handful of cells, which while they're dominant in some sense, they would leave large holes in our understanding of the soil water dynamics across the basin. And the second step is to assign one of the identified soil suites or identified suites of soil characteristics to each grid cell, and then score or rank the potential sites. So they would receive 1 point for every one of the 6 soil criteria they meet. So then you get what you get is this image on the right here, kind of this mosaic of color, and a more red or purple color is going to be a more dominant, more representative soil. So it's going to have 5 or 6 out of the 6 soil characteristics in common, whereas a yellow or lighter orange is going to be a less dominant soil. So when you're assessing sites, you can look at where your sites fall on this, and then perhaps go with one that's on a more representative soil. And then this is just what it looks like across the basin. This is a screenshot from our web map, which the Mesonettes and project managers use to view and assess various criteria, including the soils layer. And I'm just going to super briefly say that we use all these criteria to come up with these candidate site lists. They go through an assessment process through the Army Corps, go through NEPA and cultural work. And if they go through all that, then they end up on a final site list. which is what the task orders are based off of. But I don't want to take up much more time. So I'm going to say thank you for your time, and please feel free to reach out to me with more questions or feedback or comments on any of this. We do value that since you're all soil experts, and this is where you can view updates on the network. Thanks, Michael.
We had one question in the chat. Are the data from Elise, are the data available yet for the comparison of the Stevens Hydra to the climas? That was the one profile you showed.
Yeah, that data is available. That is run through Montana, and if you got in contact with me, I could get you in contact with the Montana Climate Office, and I'm sure he'd be excited to talk to you about that.
I do know that Montana recently put their Mesnet online.
Yeah, I don't know if
they
they would have put that direct comparison online. I'm sure the data is available, but I think they would be happy to share that comparison with you. What's interesting is from that picture, they originally ended up going with the Stevens Hydro probe, and then they actually switched to the Aclima because of the research that came out of the Aclima TDR probe. So they're not using either of those. They've decided to go with the Aclima, which I believe is the one that Stephen Evett just told us about.
Yeah. Okay, thank you. If there are other questions in the chat, please follow up. I have a few notes, and then we're going to take a short break. The presentation by Stephen was meant as an overview of soil monitoring technologies in situ primarily. And then we wanted to show one of the latest activities that's happening in real time. So the Army Corps of Engineers presentation is meant to show you that that networks are still growing, they're adapting and learning from other research going on out there. So we're getting a lot of, sometimes our research gets a little disconnected from the real world. This is a real world initiative trying to solve flooding issues in the upper Missouri River Basin. So it's great to see those two things. Our next session will be on, our next two sessions will be on sensor networks. We're in the in situ side right now. We'll move into some of the other technologies, remote sensing, modeling tomorrow. But before we go there, I wanted to post a chat, a poll to get a sense of who we are, and we will leave this poll up for 5 minutes, and we will take a short break, bio break if you want, and return in 5 minutes or 1:20 Eastern time. We'll go over the results of this and do the logistics and start on our next session. So thank you, everybody.